Dun, 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 da, 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 da. We're gonna do some probabilities for mean. And what makes this one a little different than what we've done before is here we're talking about a distribution that is highly right skewed, the number of children per household, because there's a lot of households that have 0, 1, 2, 3, 4 kids. But once you start getting into 5, 6, and 7, it's a little more rare. The picture for the data would look something like this. We have lots of homes with a few children, and then as you get more and more children, it becomes pretty rare. Out here at 20 children, it happens, but it's extremely uncommon. So this distribution is definitely not normal. Now what I hope you recognize is our standard deviation is actually higher than the mean. If this was normally distributed, that would mean negative numbers are very likely, which you can't have negative children, I don't think, unless this is a science fiction movie, which it's not. Welcome to statistics. You can have a standard deviation higher than the mean when you're talking about highly skewed distributions, which is why it's hard for me to show you what the standard deviation means in this case, because in one direction from the mean or the other direction of the mean, it's a different shape. It seems like this is the kind of question we would not be able to do, except our sample size is 50. That's more than 30. And there's a special theorem that says if you're doing probabilities for a mean and we're over 30, we're going to say it's close enough to normal that we can do it. So even though this is the picture of the data, this is the picture of probabilities for the mean. Notice it's centered over 2.7, and our standard deviation isn't just 3, it's 3 over the square root of 50 because we want probabilities for the mean. Now, is this actually perfectly normal? No, there would still be a small amount of skew in there because to get it perfectly normal, you would need infinite amount of data points, or you would need to start with something that was normal to begin with. But in this case, my art skills are not good enough to show how much it deviates from normal. And so in this class, we're going to say over 30, close enough to normal that we're going to treat it like it's normal. And now we can find probabilities. And this should remind you what we've done before, except all you need to do is keep track of that square root in there. So I want to know the probability of, and this is what happens when I'm recording a video and I realize a mistake partway through it. I just pause it, and now I've fixed it. I need to say or less because if I just say the average of 1.18, well, that's an exact value for a continuous distribution. I need the or less. Okay, so I want an average of 1.81 or less, and here's why it matters. The census a few years back hired people to go visit the homes of those who did not answer the census survey. I lived in Texas at the time. Some of my friends were actually hired to go into the backwoods of Texas and try to survey people. Now, imagine you're in the backwoods of Texas, and these are people who refuse to answer the survey from the US government. It might not surprise you that they would greet these census takers at the door with a shotgun and a pit bull. Are you from the government? Not really. Okay, so some census takers got scared and they just said, I'm going to guess how many kids they have without actually going to visit their property. Could you catch someone who was doing that? Well, let's say someone was hired to go out and randomly sample these 50 homes, and they had an average of 1.81. I'm wondering how strange that is. Is it so strange that I'm beginning to doubt whether they actually did the survey and could they be lying? So I want the probability 1.81. Where does it land on here? Why don't we put it right there? And then the area that I want would be the area to the left of that. So this should look like the kind of question we were doing before. It's not any harder once you understand how to handle that sample size in relation to the average. My next goal is to get a z-score, which comes out to be negative 2.098. So from here, I'm going to go 1 standard deviation, 2 standard deviations. It looks like my line is a little bit off, but that's okay, because watch what I can do to it. So that's a trick that only advanced statisticians know how to do. I want the area of that to the left, so that kind of area. Why? I'm trying to figure out whether this census taker that got 1.81 was just super unlucky or whether I think there was cheating. Well, how much area is there in this little tail? If I put in my z-score of negative 2.098, I get an area of 0.01831. So how many census takers, if they were really honest census takers, would get an average this low or even something lower? And the answer is just under 2% of census takers get averages this low just by luck. Okay, well, now as a government agency, if I tell you we can afford to investigate the 1% most suspicious, well, this wouldn't cut it. On the other hand, if I've got more funding and I say, let's investigate the 5% that are most suspicious, I'd say, let's include this guy and see whether he was being honest or whether he was cheating. And that is something we are going to focus on later. It's called a hypothesis test. That's the point and the reason why we're practicing this. The goal I want you to get out of this is that you can do a normal distribution, even if it wasn't normal to start with, as long as you have a large enough sample size. Look, it looks like I'm wearing a hat.